Okay, so last week we had gotten through kind of working into hypothesis testing and some of just the basic conceptual ideas behind that, which are important because we're going to be talking about things like rejecting the null and p-values and critical values and the test statistics and all that. So it's important to, again, refresh your memory on what those concepts are and just to kind of summarize again where we left off. So there's the null hypothesis. Again, that's that nothing's happened. There's no effect, no difference. The program doesn't work. There's the alternative hypothesis. That's our question. That's our belief. That's the thing we're interested in testing that we think we're going to see. The alpha level is how comfortable I am concluding I'm right. How comfortable am I rejecting the null hypothesis when the null is true? How comfortable am I saying this program works when it doesn't? How comfortable am I saying there's a gender difference when there's not? For behavioral sciences, we tend to set that at 0.05 or 5% of the time. We're okay making those sorts of mistakes. We don't like making type 1 errors. So we only want to do it 1 out of every 20 times. The test statistic, that's that number we calculate from our data that gets more extreme. The more extreme our test statistic, the less likely it is that the null hypothesis is true. It's just that number that we get from our data that's sensitive to whether the null or alternative is true. And it's a combination of the means and variances and the sample size. All of that combines to give us a T. Come on in. Come on in, Lisa.
I'm so sorry.
That's right. You mentioned you were driving up. So,
is that a lot? I'm in the right place.
Yes, you're in the right place. Yes.
No way, yeah.
Actually, we could have done like a little quick. Well, we'll do that in the break, being we got 2 new faces. So again, test statistics. That's our T. That's our F. Chi-squares, Z's, and their value is the more extreme they are, the further away from 0. Some can go positive and negative, and F can only go positive. We'll see that it's just an indication that it's less and less likely that the null is true. The critical value of the test statistic, you can think of it as a line in the sand that you need to cross. There's like the famous George Bush 1, kind of that line in the sand in Iraq, that if they cross, it's or a red line. We can go to Obama. Politicians have trouble with these lines and red lines and stuff. Anyway, it's the critical value of our test statistic is just that value that our test statistic has to beat. It has to get more extreme than that critical value to reject the null. It's the value that if our alpha is 0.05, it's the value that only 5% of the time would we see a test statistic more extreme. So the critical value of the test statistic is just that value of the test statistic that ends up giving us a probability, a p-value, a probability being more extreme than that, equal to our alpha level. So the critical value is closely tied to the alpha level. Right there, your critical value is going to be based on what the alpha level is. Then the p-value, that tells us kind of in a conceptual level, how likely would I have seen an effect, this big or bigger, if the null hypothesis is true. Okay. Technically, it's the probability of obtaining a result as extreme or more extreme than what we observed if the null hypothesis is true. Everything's always based on if the null is true, if nothing's happening, if we're wrong. Okay? If the p-value is less than our alpha level, so we've said I only want to screw up with a type 1 error. I only want to reject the null when it's true 5% of the time. So my alpha is 0.05. If my p-value is less than 0.05, it tells me the chance of seeing something this extreme, if the null is true, is less than 5%. So that's when we reject the null. So we want our p-value to be less than the alpha level, and we can reject the null. If it's not less than the alpha level, we don't reject the null because the chance of the null being true is too much. It's too big. Maybe it's 10% of the time. It may still be unlikely, but we've decided only 1 out of 20 times do I want to make a type 1 error. If there's a 10% chance, that's not good enough. Okay? So let's get into some test statistics. The one sample t-test. This is what you do. You do a one sample t-test when you know the population mean, mu. Remember kind of our Greek symbols we went through last time. So we know the population mean, but we don't know the standard deviation of the population. So, for example, you might know the average SAT score for everybody, but you don't know how spread out in the population what that information is. Now, often, in fact, when we do one sample t-test, it's not because we know mu, but we're going to plug in some other value for mu. There's something we want to compare it to. So mu could be the population average, but this number could also be, well, the kind of what would I expect to see if my treatment has no effect? If a variable has no effect, I expect the effect to be 0. So we'll see, you'll often do a one sample t-test, and what you're doing is you're comparing some sample average to some other number. And we'll see with regression, it's going to often be a 0, so we won't even write it. But it's kind of it's not obvious when you first look at it, but we're going to see, oh, we're doing one sample t-test all the time. It just doesn't jump out because we don't see that. But you can do a one sample t-test where you're comparing it to some other number, but we don't know the standard deviation for the population, so we can't do a one sample z-test that we're not even going to talk about. You probably did that in your 573 or equivalent. So as we talked about last week, kind of a common theme we're going to see for all these statistical tests, kind of at a conceptual level, is they get at this notion of how large of a difference did I see compared to how large of a difference did I expect. So did I see some big effect and did I see a big difference and I expected a small one, or did I see a small difference but I expected a big one? That gets at the whole notion of, again, that grasshopper. If my pet is 2 kilograms more than average, if my pet is a rhino, 2 kilograms is nothing. I expect a much more variability, rhino to rhino, than 2 kilograms. If it's grasshoppers, a 2 kilogram difference is huge. Okay? So kind of the first part of that is, how big of a difference did we see? That's simply for a one sample t-test. It's the sample average. See, this is more precise than kind of my hand just messing up the video. It's the sample average minus mu. So that's how big of a difference did I see. Here's what I observed minus what we saw, minus the population average. Then the second part of that is, how big of a difference did I expect to see? And that's the standard error of the mean. So we talked about the standard deviation, right, was how spread out individual scores are. And then last week we talked about sample averages. We know that if your the standard deviation is for individual scores, but when we're taking an average for a sample, how spread out those averages are is going to be less and less the bigger and bigger the sample is. For very large samples, the variability in our averages gets very, very small. And which is kind of wild when you think about it. Keep in mind, we're doing this. We're talking about the standard deviation of samples. But we're not actually going out there and collecting 100 different samples and calculating their means and looking at the standard deviation of those samples. We're estimating what the standard deviation would be for an infinite number of samples based on one sample. Doesn't that seem, kind of still blows my mind. The math has that ability. From one sample, we're able to estimate what we would see for the variability if we had an infinite number of samples and calculated an infinite number of means and looked at the standard deviation of all those means. That's what the standard error of the mean is. It's what would be the standard deviation of sample averages as the size of our sample. We just say standard error. On one hand, you could think, why don't we call it the standard deviation of the means? Because that's exactly what it is. It's a standard deviation. But one, that would get confusing. Now we're talking standard deviation of a mean or standard deviation of scores. But also the standard deviation for the scores, we can calculate exactly. The standard error is we're estimating it. And it's also not based on an individual score. It's based on some parameters, means or slopes or something else. So that's why we call it the standard error. But it's exactly the same. Exactly the same. I remember it was like my second stats course when I finally sunk in. Oh, wait. Because it always seemed kind of magical to me for that very reason that the standard error is based on, we're talking about this infinite number of samples based on one. So the whole thing seemed, when I first took stats, seemed kind of mystical to me, hence the one. Until it's like, oh, it's exactly like a standard deviation. Then it all makes sense. Notation-wise, so our standard deviation, lowercase s of sub x, that's just our way of saying the standard deviation of x, is the sum of squares divided by n minus 1. Take the square root, that's our standard deviation, right? The standard deviation of the sample means is just the standard deviation for the raw scores divided by the square root of n. So if our standard deviation for the raw scores is 20, and we have a sample of 100, the standard deviation for samples of 100 would be 20 divided by the square root of 100, or 20 divided by 10, or only 2. So you can see how it gets a lot smaller as your sample gets bigger. Hence, statisticians love big sample sizes, because our kind of what it takes to see when we say, I got to get a thing about, I caught a fish this big. What's the movie Dave, where he's kind of got the robotic arms? It's got to be on YouTube. Anyway, if I'm seeing something this big, and my yardstick of how big is it, which is what the standard error is, if my standard error is huge, well, that effect doesn't look that big. But if I have a big sample, my standard error is this big, the same effect suddenly looks much larger. Okay? So the t-test, the one sample t-test, is the x bar, our sample average minus mu divided by the standard error of the mean. We write that out, t and then parentheses n minus 1. Not that you literally write n minus 1, but you just put your sample size, minus 1, in the parentheses. So with a sample size of 100, it'd be t, then parentheses 99 equals whatever that solves to. Notation-wise, this is important, because you're going to have to, on the assignments, particularly like the result write-ups, you're going to have to write that out. So save yourself a resubmission, and don't write out literally t with 99 degrees of freedom. That's, no, that'll just get you. You submit that for your dissertation, one of your committee members is going to kick it back to you, or the grad school will kick it back, or you send it off for a journal, the journal will send it back, and you're just going to waste your time. T parenthesis 99 end parenthesis equals whatever the number is. Okay, let's keep going. The t distribution. Now, the t, this is what we're calculating here, our t-score, and that's called our t-score. The t-scores follow what's called a t-distribution. Again, this should still be review, hopefully, which is just like the normal curve, but a little flatter in the middle, a little thicker in the tails. But otherwise, it looks similar to the normal curve. The larger the sample size, the more a t-distribution looks like the normal curve. And in fact, if you have an infinitely big sample, it is the normal curve. But when's the last time anyone had an infinite sample size? The degree, the shape of the curve, again, varies based on the degrees of freedom. So that's another reason why the degrees of freedom are important. because if you need to know which of those t distributions are the ones is the one you're going to be using to calculate your p-value and all of that. So the larger the degrees of freedom, which as you can see, that's the degrees of freedom for the one sample t-test is equal to n minus 1. The larger our degrees of freedom, the closer the closer the t distribution becomes to the normal curve. Okay? So again, t n minus 1, I don't know if I said that in the last slide, I should have. That's our degrees of freedom, and then whatever the value is. To decide whether or not we're going to reject the null, what do? We go through, we calculate our t-score, we determine what the degrees of freedom are, which is, again, just n minus 1. Then based on that, we'd have to find out what our p-value is. Now, you can look it up from a table, or I'm actually almost tempted just to drop this line altogether, just plug it into Excel. And this is not on this is kind of something new I just added. Here's just the text you put into Excel, and it'll tell you what the p-value is. So it's you literally type, you don't type the quotes, just equal t dot dis dot 2t, two-tailed, equals parenthesis, whatever your t-score is, comma, whatever the degrees of freedom are, and parenthesis. And it'll pop back and tell you exactly what your p-value is for a two-tailed test. Okay, so you just enter that, and that's how you can get exact p's, and not even worry about trying to figure out how to use those tables at the back of books. That is like so 1990s, 1980s. I mean, it was when I was a student. Okay, if the p-value is less than the alpha level, then you can reject the null hypothesis. So, or alternatively, well, one way, are you going to reject your null is you look at the p-value, compare that to your alpha level, or you can calculate the region of rejection and see if you're in the reject region. And what that involves, you just determine what are those critical t-scores. So what are the t-scores? How big does my t-score need to be for me to reject the null hypothesis? And so there'll be a positive, assuming we're all doing two-tailed tests, there's the positive and a negative version of that critical t-score. Anywhere in between those critical t-scores, I fail to reject the null. And this is what this curve is just the probability. You can think of, that's our t distribution. It's just, the area under the distribution indicates the probability of getting a result this extreme if the null is true.
I just have a question trying to go back to when I was an undergrad taking this class. So another way that you would hear someone say something like, you could just say if it falls within the fail to reject null region, that it's not statistically significant. That's
Yes.
what you're saying, right?
Yes,
and
that's
if
right.
it falls outside of it, it is statistically
significant. Exactly.
Okay.
So here you can see if the null is true, and here's our t-score. So there's a t of 0, which is right in the middle. That's like 0 standard deviations away from that, whatever the population mean is. So anywhere in this range, you can see even if the null is true and our sample average really is equal to the population average, nothing's going on, there'll always be some random variation in our sample. The average won't. It's unlikely the average will be exactly equal to mu. So this just says, well, yeah, the results are a little different from the population average, but not enough that we're going to reject the null, because there's a lot of possibility in here. Once you cross these lines in the sand, once you cross those critical values, then notice out here, the chance of getting a result out here is pretty small. You look at that much of here's 100%, here's the total probability. The chance out here is really small. That's actually only 2.5%. There's 2.5% of that total possibility is out here, and 2.5% of the total possible outcomes are out there if the null is true. So again, kind of the idea is, and that's based on our 95%, that's based on our alpha of 0.05. We get those two critical values. Now again, you can look that up in a table, or you can get those numbers from Excel. And notice this is a little different number. Because here what we're asking, previously we were saying, let me tell Excel what my t-score is. And Excel will tell me the p-value. Now you're saying, I want to tell Excel my alpha level. I want to give, so in the previous version, the previous equation says you give Excel a t-score, it gives you back a probability. Now we're saying I'm going to give Excel a probability, in this case my alpha level, 0.05, and it's going to give me back a t-score. So it's the yin and the yang in Microsoft world. So you just write that in, and you say, well, my alpha is 0.05, here's my degrees of freedom, and it comes back and says, here's your critical t-score. And you just need to remember it's positive and negative. And then if your t-score, now you're not looking at the p-value, we're just comparing the critical t with the t-score I obtained. If my t-score is out here or out here, I'm going to reject the null. So they're both doing the same function. They'll both give you the same conclusion. They just kind of do it in different ways. This is important because we're going to get back to the notion, we're going to use these critical scores in other ways later on, and getting comfortable with the idea that it's just, the critical scores are, if the null is true, kind of how much spread, how much variability do I expect to see in whatever it is I'm estimating. In this case, how much variability do I expect to see in my sample averages? So that's we're gonna keep using those later on. I'm going to kind of just one more thing to kind of belabor this. So again, the idea is if I get a t-score way out here, remember this distribution says here's how likely all your results would be if the null is true. If I get a result way out here, you're sitting there saying, wow, the chance of that is like almost nothing. That's like winning the lottery. Has anyone here ever won the lottery? No. So what's the chance of winning the lottery? Almost nothing. So if I've got something that's so rare, am I really that lucky? No, you're not that lucky. What it is the null's not true. That's telling you you're out here because the average for your sample, your intervention average, your intervention really did work. Remember, the null is based on nothing happened. You're out here because the average for your sample isn't 0. It's not whatever the average for the population is. It's not that there's no gender difference or no program effects. It's because the null isn't true. So this curve doesn't really apply to your data. You've calculated it based on the null being true, but it's not. That's why we like being out. That's the whole idea of being in those extreme scores. The chance of seeing it so rare, we conclude I'm not that lucky. This is not reality. Reality is something else. Okay?
Can I ask a quick question?
Sure.
So if you see that your score is so far to past those critical regions that you redo it and see if your alpha could be smaller than 0.05, do people ever do that in their work to show that it not only is it 0.05, but it might also be 0.01?
Well, the p-value is what tells you. So the alpha level is just saying, here's my a priori. Now you shouldn't change the alpha. Once the alpha should be kind of set in advance, and you're saying, here's what I need, and I'm going to reject the null, because in the end, ultimately, if I set alpha at 0.04, I'd have made a type 1 error 5% of the time. Now, it doesn't actually matter how extreme the result is. 5% of the time I would have made a type 1 error. The p-value is kind of getting at exactly what you're saying. Well, I set my alpha at 0.05, at 5%. But my result is way out here. The probability of seeing a result this extreme is only 1 in 1,000 or 1 in 10,000. It's really rare. So that's kind of, they complement each other. The alpha is the line in the sand that we determine right at the beginning. This is what I've got to cross. The p-value is, did you cross it and how far did you keep going?
So how do we determine the alpha level? I mean, the most appropriate one from lit review or?
Typically, you'll determine your alpha level because it'll be your field. There'll be a standard practice in the field, or journals will kind of require it. Maybe it was my other class I was talking about. There's a debate going on in the literature now. Yes, it was my other class. That, in the field. And it's kind of funny because education is going, my concern is education is talking, well, should we have an alpha 0.05? Because what happens is, remember we talked last week about the alpha and beta, the probability of making a type 2 error. So alpha is our probability of rejecting the null when the null is true. We do that 5%. The other type, that's a type 1 error. A type 2 error is I fail to reject the null when I should. I'm right, my theory is right, my intervention works, but I fail to reject the null. I conclude nothing's happening. That's kind of depressing. We're okay making those sorts of mistakes, kind of in behavioral sciences as a rule of thumb, about 20% of the time. The tradition has been, we're okay 80% of the time. If I'm right, I want to know it 80% of the time. Power from last week, right? Making a type 2 error, I'm okay doing that 20% of the time. So there's some that have said, well, we worry too much about type 1 errors. And think of those, we don't worry enough about all those effective interventions that we're rejecting, that we're failing to recognize because they're type 2 errors. There's like an article someone wrote about, woe to the poor little type 2 error. Or maybe it was at a conference. Anyway, that we shouldn't worry about type 1 errors as much. And maybe we should loosen up our alpha level so that we don't reject these awesome interventions that are out there working and we just are not recognizing it. My response to that is bunk. It's like, no, that's crazy. I mean, one, if education was flooded with if we had all these effective treatment interventions and programs that were working that we weren't recognizing, education was very different. I mean, a lot more kids would be reading a lot better than they are. So I don't think we have a problem of too many effective interventions not being recognized. We have a problem of too many ineffective interventions being said that they're effective. We have too many type 1 errors, not too many type 2 errors. And they go hand in hand. If we loosen up our type 1, if we lower the type 2 errors, we will increase our type 1s. There's that balance between the two. So while you've got some in education arguing, we need to lower, they're not saying this language, but mathematically what they're saying is, we need to increase our alpha level, we need to make more type 1 errors. Everyone else across the spectrum, I think most fields are saying, maybe 0.05 is not big enough. Maybe 0.05 is too big. Maybe we need to have a standard alpha of 0.01 or 0.001. Because you see, and you may have seen I know I'm digressing, you may have seen in the news, or kind of the science, the geek news, there's been a series of studies the last few years where people have gone out and tried to replicate experimental results, particularly in the behavioral sciences, and they don't replicate. There was one actually a few weeks ago, I think they looked at a total of almost 50 different well-studied, kind of very strong studies, they thought, very clear effects. Less than half of them replicated when someone went in and tried to do it. There's a whole nother conversation about how can that happen. I mean, there's a variety of issues, selection bias, that all the studies that say nothing happened never get published. There's also some interesting statistical issues that come into play that are also related to the fact that why is it that all the pollsters thought Hillary was going to win and she didn't? That actually is kind of related to the same problem of why are these studies not replicating? But we don't need to go there. But the point is, and I really digress, but it's an important point, particularly for everyone in education, because we're going the wrong direction potentially, or at least there's voices in education calling us that siren swan song. What's that?
Siren song.
Yeah, that they kind of call it that ships to the rocks to rest.
Siren song?
Yes. Okay. I'm sorry. The
No, siren song.
siren song. Yeah, but there was a name for this. What was that? Anyway, we do not want to fall prey to that. Okay, let's. I digress. But anyway, so yeah, the type 1 and type 2 error go hand in hand. So how do we decide? It kind of depends on the field, and there's some that are saying we need to drop 0.05, we need to go to 0.01. I think we may see that happening more.